Well, hello there and welcome. This is going to be a video lesson brought to you by Triad Math, Inc. about a subject that has fascinated men and women for well over 2,000 years, and it's called Zeno's paradox. Now, I'm Craig Hane, and my students call me Dr. Dell, and I'm the creator of the Practical Math Foundation course and the 10-tier program, which is a high school math curriculum that works for all students. And I've described this in great detail in my book, Teaching Math, which you can get a free copy of by simply going to triadmathinc.com and downloading a PDF version of it. Now, this video lesson is aimed specifically at those students that have completed Tier 4 of my program, which is the treatment of algebra, geometry, and trigonometry and other topics for STEM-bound students that are going to top-notch schools. And it is designed to take advantage of some of the things they've already now learned in Tier 4, but also to point the way to things they're going to be learning in the tiers to come, 5, 6, and 7, as they further their math education. Now, Zeno's paradox is a very fascinating thing. The Greek Zeno believed that if you took a series of numbers that was infinite in duration, a1 plus a2 dot dot dot, and those ellipsis dots mean this goes on forever. Using a summation notation, this would be I equals 1 to infinity of a sub I. They believed that any such sum was actually equal to infinity. This would be infinite in size. And because of that, they derived three separate paradoxes. Now, in particular, they believed that the sum where you had 1/2 plus a fourth plus an eighth and so on, where you double the denominator every time, that sum had to be infinity. And of course, that led them then to the so-called Zeno's paradoxes. And this, of course, then is what modern mathematicians have resolved. And we're going to be talking about that in this video, as well as some additional, really, I consider very unsettling facts about infinite series. Now, as all my Tier 4 graduates know, I like to combine geometry and numbers as much as we can to get a geometric visualization as well. So let's look at this infinite series here geometrically. We start here with a scale where we got 1 here and 1 here, and we come across, this would be length 1. Then we drop down, vertically down to 1/2. Then we make another right angle and go back. We're always going to go clockwise, and this would be 1/4. Then we make another right angle and come up. This would be an eighth. Come over. This would be a 16th. Of course, that's 1/2 to the 4th. Then come back down. And you just continue that spiraling process indefinitely. Now, it turns out there's a limit point that this will spiral down to, and that turns out to be the point 4/5, 3/5, which I would expect any Tier 4 student to be able to derive that right now. Now, one of the things I want to point out about this is that this will scale, just like we're going to learn to do in fractal geometry. Suppose you put a little box around this and expand it, and so then it would look like this. You come across, let's say we've done this 32 times. So you got 1/2 to the 32nd power, then you come down 1/2 to the 33rd, 1/2 to the 34th, and so on. And in general, if you have the nth power, you come over 1/2 to the nth, down 1/2 to the n plus 1, back over 1/2 to the n plus 2, up 1/2 to the n plus 3, and so on. And again, it's a spiral. So you can just keep magnifying in on this, and there's no limit to how far this will magnify in. And that's the kind of thing we do, and we're going to learn to do in what's called fractal geometry. Now, because these line segments are getting smaller and smaller and smaller, even though you're adding them up and to an unlimited number, it appears like if you look at the total lengths of these things as you continue down this spiral, that it could be infinite or it might be finite. And of course, our ancestor mathematicians about 300 years ago were able to prove that this total length, as you did this spiral, was going to be finite, which of course is pretty intuitively satisfying. Now, in Tier 4, you learned about geometric series. A plus AR squared plus dot dot dot. Here's the summation notation for it. I from 0 to infinity of A, R to the I power, will sum to A over 1 minus R whenever the absolute value of R is less than 1. Now, in particular, if we apply that to this geometric series we just had, 1/2 to the I, and this time we'll start with I equals 0, so the first term will be 1, then it's going to sum to 1/1 minus 1/2, or 2. And that resolves Zeno's paradox. That's what our ancestors did about 300 years ago. And as a matter of fact, let's suppose you've gone down 100 segments. Then you're going to have 1 plus 1/2 up to plus 1/200. And how close will that be to 2? Well, the answer you can easily derive is going to be 2 minus 1 over 2 to the 100 power. So you're very, very close to the limit of 2 as you go down. And as a matter of fact, when you get down to 1 over 2 to the 100, you're down about atomic lengths now. If you started out measuring, say, in feet, you're going to be down into atomic lengths. So for practical purposes, this is going to be about as far as you can go. However, mathematicians like to consider things going on forever, infinite they call it, and so if you consider this to be an infinite series, it will eventually be exactly 2. As long as you truncate it before you get to the end, it'll be a little bit less than 2, but as you can see, it's going to get very, very close to 2 as you go down. Okay, now, for you Tier 4 students, what I want you to do is some exercises now. I want you to prove that that limit point where this thing will converge is 4/5, 3/5. Now, here's what you need to do that. When x is greater than 1, you know that 1 over x to the I power, I going from 0 to infinity, is going to be x over x minus 1. This comes from what you know about geometric series. Because x is greater than 1, 1 over x, which will now be the ratio, is less than 1. And so what we're really doing here, we're doing a generalization of this. Instead of coming down 1/2, we're coming 1 over x, where x is greater than 1. In other words, this works for all sorts of numbers, not just 1/2. Now, when x is greater than 1, if you put in an alternating series here, make this minus 1 to the I power times 1 over x to the I, so that now you're alternating. You're going 1 minus 1 over x plus 1 over x squared minus 1 over x cubed and so on. That's going to sum to x over x plus 1. And you're going to need that fact when you try to calculate that. Now, when you do this exercise by simply setting up the proper series, you're going to find that the AB for an arbitrary x is going to be x squared over x squared plus 1, comma, x squared plus 1 minus x over x squared plus 1. This is going to be very easy for you to do now. And of course, in particular, if you plug in x as 2, this is going to be 4 over 5 and 3 over 5. That's where the 4/5 over 3/5 came from. Now, these are very easy exercises for you Tier 4 graduates. You've done much harder problems than that by now anyway. Okay, so about 300 years ago, our ancestors developed the mathematics you just looked at that resolved the Zeno paradoxes. Paradox means apparent contradiction, and we found out they're not because those infinite series we just looked at converge, they say, have finite sums. So now let's look at another example. Let's start up here with the same graph, 1 and 1, and we're going to go over 1. We're going to come down 1/2, just like before, but now we're going to go over 1/3. And then we're going to go back up 1/4, and then come back over to the right 1/5, and then down 1/6, and then back over 1/7, and we're going to continue that. So now we're using the series 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. And that's also going to converge now to a point I'm just going to call AB for now, and that'll converge. You're going to get a scaling effect just like we did before for a large number n. If this comes across, this is 1 over n. This will be 1 over n plus 1, 1 over n plus 2, back up 1 over n plus 3, n plus 1 over n plus 4, 1 over n plus 5, and so on. Again, we're coming down, converging to this point AB. And it doesn't matter how large n is, we can always scale. This is what we do in fractal geometry. We scale. No matter how much you expand this out, no matter how large n is, this is going to look the same. Don't you see how what we mean by scaling this always looks the same no matter how much you magnify it? Now the question is going to be, okay, these lines are getting smaller and smaller too, so are they going to converge to a finite sum like our last example did? Or do we now have a different kind of situation? Well, we can do some calculations. If we add up the first 83 of these terms, we get over 5. Now, if we add over 12,000 of them, we finally get up to 10. And as a matter of fact, we got to add 250 million of them just to get up to a sum of 20. Now you're down about the size of an atom. So now you've magnified this out to where your lengths now are the width of an atom. And you're still going to continue this on. Now, as Keith Devlin points out in his great book, mathematics is based in the physical sciences and is a model for physical scientists, but it's a theoretical abstraction. So mathematicians allow this process to continue regardless of the size of the atom or any physical measurement. This just goes on and on and on. So the question now, you've got to ask yourself, well, what's going to be an upper bound for this? If it takes you 250 million to get over 20, goodness, what's it going to take to get over, say, 40 or 100? And indeed, can you just get over any number you want here? What's the deal going to be here? How large can this get? I mean, after all, you're down to the point where these line segments are smaller than an atom, and they're getting smaller every time as you go around. They get smaller and smaller and smaller. What can this all possibly add up to? Now just pause the video and think a little bit about that, and then we're going to discuss it. Well, what would you say if I told you that if you go out far enough, this will go over 40? And then if you go even further out, make this even a bigger number out here, it'll go over 100. As a matter of fact, what would you say if I told you that if you make this large enough here and go on far enough, even though these little segments are extremely small, you can go out 100 million miles. You can go over 1 billion. You can go over 1 trillion. In fact, no matter what number you give me, if I go far enough out in this series, this sum will exceed that number that you gave me. Now just stop and think about that. These are getting smaller and smaller. They're spiraling in, just like the previous example did. But instead of the length approaching some limit, it's just getting bigger and bigger and bigger, even though the segments themselves are getting extremely small. Now, quite frankly, I found this very intuitively difficult to swallow. But this is the type of thing that happens when you get into infinite type situations. And I'm going to talk to you a little bit more about that and why that is now and how mathematicians deal with that. Well, what you're going to start learning when we get into Tier 5 and beyond is that there's a concept of limit. And so the question is, does this series have a limit sum? Is there a total length going to be there? Is there an upper bound? And the answer is there's no upper bound. In fact, the total length is infinite. And this was discovered way back in the 1300s. The very first mathematician we know was a Frenchman. And here's how he did it. He said, well, take 1 plus a half, then you got plus a third, plus a fourth, and so on. Now take a third and a fourth, that's greater than a half. Then you take the next 4 terms. 1/5, 1/6, 1/7, 1/8, that's greater than a half. Then you take the next 8 terms, 1/9 up through 1/6, that's greater than a half. And as a matter of fact, if you're out at 1 over 2 to the nth plus 1, and then you add 1 over 2 to the nth plus 2, dot, 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 up to 1 over 2 to the nth plus 2 to the n, these are 2 to the n terms, 2 to the n power terms. Now this term right here is greater than 1 over 2 to the n plus 1, because 2 to the n plus 1, see, is bigger than 2 to the n plus 1. And this term here is greater than 1 over 2 to the n plus 1. Same reason. In fact, all these terms here, except the final one, are greater than 1 over 2 to the n plus 1. And how many of them are there? There's 2 to the nth of them. So you got 2 to the nth times 1 over 2 to the n plus 1. That's 1/2. So all these terms are greater than a half. And that's for any n. So you just keep going. And out you go. In fact, what has happened is, in effect, is we took the series we had before, 1 plus a half, then we had plus a fourth, and plus an eighth, and plus a 16th, and we've interpolated a bunch of other terms in it in such a way that it causes this bulging effect, and it causes this infinite expansion. And so that really is the proof and the explanation of why this limit is infinite. Okay, now I want to give you, Tier 4 students, an exercise. I want you to find that limit point, a over b. Now, here's what the answer is going to be. I always give you the answers. A is going to be pi over 4. Wow, how did pi get into this thing? And B is going to be 1 plus the natural log of square root of 2 over 2. You might ask yourself, my goodness, how does this natural, what's called harmonic series here, get involved with pi, which comes from circles, and get involved with natural log, which comes from exponential growth, and the number e? And that is really quite fascinating. So I challenge you to stop the video and do this problem before you come back and watch the rest of it. And then I'm going to give you a hint and talk a little bit about the future tiers. Well, when you go through the same argument you did before, you're going to come into these two series. 1 minus a third plus a fifth minus a seventh and so on. And if you go to Wolfram Alpha and look that up, I don't expect you to know it now, it turns out to be pi over 4. And this series, 1 minus a half plus a third minus a fourth and so on, turns out to be the natural log of 2. And Wolfram Alpha will tell you both of those. Now, you're going to be able to prove right away that A is this series here. It's pi over 4. B is a little more complicated, a little more work. It's going to end up being 1 minus 1/2 natural log of 2. And if you use the facts about logarithms, you get down to 1 plus natural log of square root of 2 over 2. And so that's going to be the answer. So those will be a real nice exercise for you Tier 4 grads. Okay, now in the future tiers, we're going to be talking about fractal geometry, among other things. This is the geometry of nature. It's not a smooth geometry. It actually has fractional dimensions instead of ordinary Euclidean And even the standard non-Euclidean geometries are smooth with integral dimensions. You're going to have scaling. You're going to have boundaries with infinite length around finite areas. So this is all very fascinating, and this is sort of a preamble or a prelude to that.